Today, you're going to learn how to accurately measure distance from any angle looking towards a target using a Limelight camera and an April tag. Let's do a measurement from our Limelight over to the target. I'm looking about 123 and I'm pushing out about 122.5. I'm Brogan and I'm teaching robotics and design for over a decade now. And today I'm going to step you through how the math of this works to be able to find out what our exact distance is, how you can find the information you need to be able to solve this out using a CAD program. And then I'll show you how to code this step-by-step inside Java before we actually do a practical example so you can see just how far away your distance is. And when you change angle, that distance still remains accurate. So first, let's talk a little bit about how this method actually works to be able to find distance to a target, no matter what angle you're looking at, to be able to see your April tag. So let's start with an example of looking at a basketball hoop. There's a bit of information that you already know. You already know how high you are, your height and the height of your eyes to the ground. You also know the height of the basketball hoop. Depending on what regulations you're playing, the goal or your target for the hoop is going to have a specific height from the ground plane. So you know your height and you know the height to the basketball hoop. You also know what angle you have to tilt your head at to be able to look directly at that hoop. And if we know all three of those pieces of information, then we can figure out how far away it is from my eyes to that target. Because the Limelight will only return to you the angle you have from the target on your TX, which is, of course, your angle looking at this way, and your angle on the TY, which, of course, your tilt up and tilt down language in relation, or angle in relation to that target. As long as we know the heights of our camera and the height of our target or our goal, we can do a little bit of geometry to be able to figure that out. Because when we know what that vertical angle is, or that tilt of our head, there's really only one distance that it can be from far away. If you think about it, if you're really close to that basketball hoop, you have to have a very high target angle. If you're very far away from the basketball hoop, you have to have a very low angle to be able to look at that basketball hoop. So regardless of where you are looking at, provided you're looking directly at that target, there's only one possible distance it could be for you to change the angle of your head, or the TY that gets returned. So looking at Limelight's official documentation here, we have height 1, which is the height of our eyes, or the height of our camera lens. We have height 2, which is the height of our target, where it is we're trying to get to, or in this case, the April tag. We also know the angle of our lens in relation to the ground plane, and the angle of our head in relation to the target. What we don't know right now is we don't know the distance. But given that we know all this information, we should be able to just simply use a little bit of geometry to be able to know what our height difference is, to be able to know what our angle 1 and our angle 2 is for our total angle towards the target, to be able to find out that eventual distance. But how do we make sure that we know what the angle is from our camera to the ground plane, as well as the height to the camera on the ground plane? So in order for this method to work, we need to know two bits of information that likely you need to get from a CAD program to be able to get the amount of accuracy you need to be able to get down to that centimeter-ish accuracy. We need the height from the ground plane to the height of the lens on the camera. We also need the angle of the camera in relation to that horizontal ground plane. So for me, I've just got a very simple setup here. I just have it set up in a corner. It's probably not the best place to have things set up on your Limelight, but it doesn't really matter because we can change where our goal target is. Just keep in mind that it's going to return values from the Limelight itself, unless you've done some offsetting. So Limelight has this little piece of glass in here, so I'm just going to go ahead and hide this picture here just so that I can be able to get a view of that glass. And what I'm going to do is I'm just simply going to grab my inspect tool. I'll grab from my ground plane that I've drawn to make sure that it is from the bottom of my wheels. And I will grab the outside edge of my camera lens, which is this guy here. And my distance is 186.4. And then that actually is only grabbing to the bottom of my circle here. So I probably need to add in the distance there. So 186.4. And if I were to again inspect this, that has a radius of 0.59 or 0.6. Which means I'm actually 185 up on the ground. So I'm going to go ahead and note that down so that I can use that later. The other thing I need to be able to figure out is the angle from the ground plane. Oops, let's change that again. There we go. So now I need to figure out the angle above horizontal that my Limelight is. Now my Limelight's not a huge difference here. You can get from the angle, or you can get it from whatever your mount is, whatever have you. just so we have that knowledge. So I'm going to go again, open up my inspect tool, grab from this face, and I'm going to just select the outside face here. And my angle off of the horizontal here is not 82.5, it's actually opposite. So I actually want to imagine I've got a right angle here from 90 degrees over this way. And I want to measure how far I've tilted up off of that 90-degree angle here. So if I take 90 minus 82.5, I end up with 7.5 degrees for my angle. You likely need to make this a little bit more extreme. Mine is just for example purposes. And when you get really close to the target, mine's actually not capable of seeing an apolitic that's quite high if I'm far too close to the target. So you likely need to have a greater angle than I do. So with those two numbers in hand, we can now actually start getting to programming. So for this simple tutorial, again, this is not a tutorial on how do you actually set up your pipelines correctly, be able to read apolitics or doing all of that calibration. Instead, I have a tutorial down below that you can take a look at if you don't have your pipeline set up. So I'm going to make a simple class here. I'm going to make a new Java class. I'm going to call this one Limelight Distance. And inside this, we're going to extend the op mode. And every single op mode class in FTC programming needs two loops. We need a public void init and need a public void loop. And for Limelight, I also like to put in a public void start. And this method gets called whenever you push the actual play or the start button on your program. And this is where I actually like to start up the Limelight so that I'm not using a whole bunch of energy while I'm just sitting inside of an initialization loop, because it can take up a lot of energy. So we are going to make a new private Limelight 3A called Limelight 3A. And then we need 3 doubles here. So I'm going to make a new private double called camera underscore height underscore centimeters. And again, you could do this in inches. The mathematics is the exact same. I just happen to use inches in this case. So mine is 18.5 centimeters because that's what I measured off from the CAD, from the ground plane to the center of that lens. And we're going to make another private double called camera underscore angle. And our angle is 7.5 degrees. And then we also need another one called, we'll make another private double called goal height. And for your goal height, this can really be whatever it is you're looking for. So whatever the center of your April tag, in my opinion, is where your goal height should be. So I'm recording this during the time of the decode season. So if I were to take my goal here, I go from my ground plane to the top of the goal, which is 98.45 centimeters. And then I can subtract down to get to the center of my April tag, which is 23.5. And that gives me 74.95. So my goal height is 74.95 centimeters. And last one in here is a private double called distance. And we'll initially set this to 0 because this is what our actual distance is going to be. Now, as with all Limelight programs, of course, you have to actually create it. So I'll make my Limelight 3A is equal to a hardware map.get. And this is going to be a Limelight 3A.class. And then I have called it Limelight in my configuration file. Make sure you have it set up in your configuration file. Oops, and this should not be Limelight. That should be a capital Limelight 3A. And then we're also going to say Limelight 3A.pipeline switch. And the pipeline that I've used is 0 for this April tag example. And you should always start it up. And I like to do that inside of the start method. You may find this adds a slight delay to your program. However, in my opinion, it's a little more beneficial to not have that massive battery drain because the Limelight is a very power hungry tool and it might be at max 100 milliseconds. Some people have said that there's more delay on that. I think it really just depends on your specific setup. So if you find there's too much delay, feel free to move this start back inside that init method. Now let's make a new method to actually get that distance. So I'm going to make a public double called getDistance. And in this, I'm going to pass in a double called ty so that we can get our target angle on the y-axis away from that. So we'll pass that in from our Limelight. We'll make a new double called angle to target. And this is our total angle to our target. So what we have to do is we have to take our camera angle and we have to add in our ty. which is what we're going to pass in so we can get the total angle that we are in relation to our target. We also have to get the height difference between our two values here. So we actually have a new double here called height difference. And this is equal to our goal height minus our camera height, because we need to factor in the height off of our camera from where our calculations are. At this point, I'm simply going to return our height difference divided by the math.tangent of our math.2radians, and then this one is our angle to target. So effectively, these are the calculations we talked about earlier to be able to find that length of that hypotenuse across from where the distance to our target is. So now inside of our loop, we're simply going to make a new Limelight result called Limelight result, and this is going to be equal to our Limelight 3a.getLatestResult. And then if our Limelight result is not equal to null, and our Limelight result dot is valid, so if we don't have a null return and we have a valid response, this is where we're going to assign distance is going to be equal to our getDistance method, and we'll pass in Limelight result dot getTy, and then we're simply going to print out. And then we'll say our telemetry dot add data, and we'll call in distance, and then we'll pass in our distance value here. And then we'll say else, this is we don't have a valid target. We can say, telemetry dot add data, and we will say no valid target found, so that we don't end up returning that. And that's it. Super simple to get your distance set up. Let's go take a look at that in practice. So let's go ahead and boot up our program here and take a look at what our distance is. So if I were to measure across the floor here, I end up at about 143, and this is measuring about 143.7, so actually pretty darn accurate. And if we were to move a little bit closer, so we're still seeing it, because I'm so close, we'll get it again. And I measure about 129, and I'm getting about 128.2 on this one. And of course, just measuring a straight doesn't actually help, so let's get ourselves in on a more major angle. I'll make sure I can still see my target. And I might move over here just so we can still have our target at an angle while still looking at it. So let's do a measurement from our Limelight over to the target. I'm looking about 123, and I'm pushing out about 122.5. So overall, pretty darn accurate, even at an angle in that respect. Now, again, you're not going to get absolute accuracy plus or minus 1 centimeter, but this is still pretty accurate even at angles, and that's good enough for most of the distances that we need. Of course, a lot of those measurements, distances, can be attributed to the fact that my April tag's not actually on the wall. It is about a centimeter off the wall with some pieces of cardboard, and then I'm kind of roughly eyeballing where I am in there, so I'm not able to get this fact. If you find that this is not working, what you're likely is wrong is likely your camera angle is wrong. 1, make sure you have the correct distance to the center of the lens, and 2, make sure you got the correct distance on the center of your April tag, not to the top, not to the bottom. Another thing that is common that goes wrong here is that what you think may be on CAD may be different in real life. So for instance, if you look at this angle here, I'm capable of changing it by almost 2 or 3 degrees, which is pretty significant. So if you are able to shake and rotate your Limelight or bend the aluminum mount that it is on, that is also going to significantly change your accuracy. So make sure you have a very robust, stable mount, unlike the one that I'm setting a poor example with of not having a robust angle. Because even though on CAD it might show up one, the reality might be a little different. And what you can do to help solve that, to be able to measure these things in real life, is you can put your robot straight onto the target, put yourself at a known distance. So for instance, you might set yourself at 150 centimeters as a known difference, and I'll put an equation up on the screen here so that you can figure out what the actual angle of your Limelight is based off of that scenario. If you're looking for more robotics tutorials, more resources, things like that, you consider joining my community down below. And if you got any questions about this, let me know in the comments. I'll try my best to try to answer them for you. And as always, best of luck on your next robotics project.